Hi, I'm Tim Komar, and today we are going to talk about continuity and recognizing discontinuities. This is a topic from a beginning calculus course. So let's get started here. Informally, a function is continuous if its graph can be drawn without lifting the pencil from the paper. We state this definition as follows. While a function f is continuous at the point x equals a, if the limit of f of x as x approaches a equals f of a. That's what we see in this picture here. The black dot indicates that at f of a we have a function value here, in this case, of 3. And we see that the trend from values of x coming in from values less than 2 is also going to be 3. And if we look at function values coming in as x approaches 2 from the right-hand side here, is also going to be 3 over here. So the limit exists, and the function value exists, and they're equal. And to repeat what we had just said over here, encoded in that definition that we stated on the previous slide over here, there are 3 things that we need to pay attention to for the limit to exist. First of all, again, the function value exists, the limit exists, and the limit and the function value are equal. If any of the 3 conditions fails, we say that the function f is discontinuous at x equals a. A good way to begin to understand the concept of continuity is to study examples in which continuity fails. So we say a function f has a removable discontinuity at x equals a if the limit of f of x as x approaches a exists, but the limit does not equal the function value f of a. If f has a removable discontinuity at x equals a, then we can make f continuous at x equals a by redefining f of a to be that limit. Here's an example. Let's show that the function f of x defined by x squared minus 9 over x minus 3 has a removable discontinuity at x equals 3. And then let's go ahead and define f at x equals 3 so that f is indeed continuous at x equals 3. So the graph of f is shown in this figure down here, and we can observe that x is not defined at x equals 3 because if x were to equal 3, then that denominator would be 0, and this expression wouldn't be defined. So the graph here is in red, and this blue little circle again indicates that the function is not defined here at 3. It's pretty clear from the picture over here that the limit as we approach 3 is going to be 6, even though we have no function value. And we can compute here. We can factor the x squared minus 9 as x plus 3 times x minus 3 and cancel out the x minus 3's. And we're left with the limit of x plus 3 as x approaches 3, and that, as we saw on the figure on the previous slide, is going to be 6. So f has a removable discontinuity at x equals 3, and then we can define f to be 3 at 6 so that it's indeed going to be continuous there. Here's another example of a removable discontinuity. Let's show that this function g of x, defined by the square root of x minus 2 over x minus 4, as long as x is not equal to 4, and 1/2 when x equals 4, has a removable discontinuity at x equals 4. And then let's redefine g at x equals 4 so that it's indeed continuous there too. So the graph of g is shown in this picture over here, and the graph is this red curve with that missing point here at 4 and that extra point here at the point 4 1/2 to indicate how the function is defined at 4 over here. And we can see again that even though the function value is 1/2, it looks like the trend of the function values looks about to be 0.25, 1/4. So we can compute that over here directly and actually factor that x minus 4 in the denominator here to be the square root of x minus 2 times the square root of x plus 2. We can then cancel out the square root of x minus 2's on top and bottom, and we're left here with computing the limit as x approaches 4 of 1 over the square root of x plus 2. And that, again, is simply going to be 1/4. Thus, the function value and the limit at 4 are not equal, and g has a removable discontinuity at x equals 4. We can make g continuous at x equals 4 by redefining g of 4 to be 1/4. A function f has an infinite discontinuity x equals a if at least one of the following holds. That is, if one of these one-sided limits is either going to be infinity or negative infinity as x approaches a. And I've included here the limit coming in from both sides as well, just for completeness here. But all we need is at least one of these 4 here on the left. And again, remember, infinity is not a number. It is describing behavior that is either increasing without bound if it is equal to infinity here, or decreasing without bound if we have a negative infinity here. So that is, f has an infinite discontinuity at x equals a if f either increases without bound or decreases without bound as x approaches a from at least one side of x equals a. So observe that the definition of an infinite discontinuity of a function at x equals a is equivalent to the graph of f having vertical asymptote at x equals a. So here's an example. Let's show that the function f of x, which is 1 over x squared, has an infinite discontinuity at 0. So we can observe from the graph that the limit of 1 over x squared as x equals 0 is going to be infinity. In other words, the function values are increasing without bound. And we see that as we come in from the left, the values are shooting up toward infinity, and as we come in from the right, the values are also shooting up toward infinity. Otherwise, we can say increasing without bound. So f has an infinite discontinuity x equals 0. And again, we can see from this figure here that the graph of f does indeed have a vertical asymptote at x equals 0. Here's another example. So let's show that the function g of x, defined by natural log of the quantity x minus 1, as long as x is bigger than 1, and negative 1 when x equals 1 here, has an infinite discontinuity at x equals 1. So we can certainly observe from the graph here that as x approaches 1 from the right, the values are going to be decreasing without bound, in other words, negative infinity here for that right-hand limit at 1 over here. So from which we can conclude that g has an infinite discontinuity at x equals 1. Well, remember we defined the function to be negative 1 at 1. That has no impact on the infinite discontinuity here. No impact at all, because we have an infinite limit on one side. It's enough for an infinite discontinuity. And as I just said here, it is important to emphasize that even though g is defined at x equals 1, the function value g of 1 equals negative 1 is irrelevant when we're looking at that right-hand limit at x equals 1. And yes, the graph of g has a vertical asymptote at x equals 1. Take one last look at it. A function f has a jump discontinuity at x equals a if both the left and right-hand limits of f at a exist, but they're not equal to each other. Here's an example. So let's say f of x is defined to be -1 for x less than 0 and to be 1 for x greater than or equal to 0 here, which again is graphed in this figure over here. Well, we see that the left-hand limit is going to be -1. We see that the right-hand limit here is going to be equal to 1 over here. And that's enough to say that we have a jump discontinuity at the point. Both the left and right-hand limits exist as numbers, but they're not equal. We can also talk about a slightly stranger example of a discontinuity, an oscillatory discontinuity. And this is one that does not fit into the categories above of removable, infinite, and jump discontinuities. And here we have one at x equals 0 for the function sine of 1 over x. Well, the values of f of x here approach every number in the interval from -1 to 1 in an oscillatory manner. And what that means, the values are going up and down and up and down and up and down and up and down infinitely, many times, in between -1 and 1 as x approaches 0 here. Well, since we're not approaching one unique number over here, again, certainly a limit doesn't even exist in this case over here, and that function is clearly not even defined at 0. For discontinuities, here's an example to recognize discontinuities that we've just talked about. So with the function f defined on the interval from -4 to 4, given in this figure below, let's identify its discontinuity. And let's note that on the interval from -2 to 2, except at the point 0.5 over here, the function is defined by the square root of 4 minus x squared. In other words, this is a semicircle of radius 2 here. If you want to try this on your own first, please go right ahead, and then I will continue here. So let's look at -2 first. Well, we see at -2, the left-hand limit is going off to infinity over here. In other words, it's increasing without bound, and we have an infinite discontinuity there. And as we said before, whatever is happening on the right-hand side here, even though it's we actually have a finite function value and limit on the right-hand side over here, still have an infinite discontinuity at -2. At x equals 0.5, we can compute over here that the limit is going to be the square root of 15 over 2. And that's where the little blue circle is over here on the semicircle here, that we're indicating that that particular point is not on the graph of the function. But we know that the function value here of 1/2 or 0.5 is going to be at a height 4 over here. So again, since the limit exists, but it's not equal to this function value, again, we have a removable discontinuity there. At x equals 2, the left-hand limit we can see is 0 from the picture, and we can see that the right-hand limit is going to be +2. Since both one-sided limits at x equals 2 exist, but are not equal, we have a jump discontinuity at x equals 2. Here is a useful little theorem that describes that most functions with which you're familiar are indeed continuous where you want them to be. So the following functions are continuous at every point in their domains: polynomial functions, rational functions, trigonometric functions, inverse trigonometric functions, exponential functions, logarithmic functions, and root functions over here. And you might say, well, rational functions aren't defined in numbers that make the denominator 0. oh yeah, those numbers that make the denominator 0 are not in the domains. And same goes with trig functions. There are numbers where trig functions are not defined, but those numbers are simply not in the domains. So these functions that are listed here are continuous at every point in their domains. Here's a type of question that you might see in a calculus course or on an EP calculus exam. Let's find the value of a so that this function f of x here, defined as a times x plus 4 for x less than 2, and x squared minus 2 for x greater than or equal to 2. If you want to try this on your own for a moment, go right ahead. So for our solution here, the function f is clearly continuous for x less than 2 or for greater than 2 because it is defined by polynomial expressions on these intervals here. So for f to be continuous at 2, we need the limit at 2 to be equal to the function value at 2, which we can also write out as follows. That the left-hand limit equals the right-hand limit equals the function value. Well, from the definition of the function there, coming from values less than 2, the limit is simply going to be 2a plus 4. And the right-hand limit, which is actually going to equal the function value here, because remember that other definition was for x greater than or equal to 2, is simply going to be that 2 squared minus 2, or just 2 over here. Equating these, we have 2a plus 4 equals 2, from which we conclude a equals negative 1. Again, I'm Tim Komar. I'm a professional math tutor. I'm a retired mathematics professor. You can get a hold of me at that email address. There's my tutoring website. I tutor for all high school and college math courses, as well as some middle school, AP Calculus, AP Stats, AP Pre-Calculus, SAT and ACT exams, and anything else that might interest you. Thank you for listening, and have a good day.